Welcome to The Explainer. Today, we're diving into the extreme, high-stakes landscape of the 2026 tech job market. We aren't just looking at the wild frontiers of tech, we're actually going to break down the highly specific cognitive habits you absolutely need to survive in it. If you want to know exactly what it takes to thrive at the absolute bleeding edge, well, you're in the right place. $1.38 million. Seriously, just let that sink in for a second. That is the staggering average annual total compensation for cryptography professionals in 2026, according to recent verified market data. And look, we're not talking about a few lucky tech founders here. We're talking about highly specialized engineers and architects who are commanding unprecedented, literally world-class value. To put that massive number into perspective, let's compare it to the absolute most elite artificial intelligence roles out there today. Cryptography compensation spans from about $274,000 all the way up to an astronomical $5.76 million. Meanwhile, over at frontier AI labs like OpenAI, the pay is obviously highly lucrative, but it's distinctly tiered. A research scientist pulls in somewhere between $771K and $1.47 million, while a research engineer makes between $249K and $530K. It's a huge financial gap, right? And understanding the exact skills you need to access these very top tiers is exactly what we're going to unpack today.
So, here's our roadmap for the Explainer today. We've just touched on elite tech salaries. Next, we're going to cover the AI interview paradox, how to keep your edge, choosing your AI path, and finally, we'll wrap up by looking ahead at the quantum horizon.
All right, Section 2, the AI interview paradox. Or, in other words, is your AI tool secretly erasing your skills?
Have you ever stared at a blank screen during a high-pressure interview and just completely blanked? I really want you to consider this for a second. Is your heavy reliance on tools like Claude Code or GitHub Copilot secretly making you worse? Because across countless mock interviews, a really clear, kind of scary pattern has emerged. The engineers who lean on AI coding tools the heaviest, they usually have the widest gap between what they can verbally describe and what they can actually implement on a blank screen. They freeze. And it's not because they don't know the answer, but because their daily tools have completely removed the natural friction of typing it all out.
So what's actually happening in our brains here? It boils down to a concept called cognitive offloading. When AI constantly removes the friction of thinking, your brain just stops doing the heavy lifting. This actually ties directly into something called the generation effect. It's a psychological principle proven all the way back in 1978, showing that you remember information you actively generate way better than information you just passively read. Recognizing an AI's correct code is simply not the same mental operation as retrieving that complex syntax from scratch. And remember, technical interviews are almost entirely tests of retrieval.
This loss of friction leads to three really specific failure modes that quietly but relentlessly erode your skills. First, you might find you can easily talk through a beautifully clean solution, but then you completely stall on the actual loop conditions when it's time to type. Second, maybe you trust a library's behavior completely, but you'd have absolutely no idea how to reconstruct its underlying logic if an interviewer actually asked you to. And third, and this one is super common, it's the physical habit itself. You know, pausing at the exact moment a suggestion would normally pop up, just waiting for an autocomplete in an environment where it simply doesn't exist.
Okay, so how do we fix this? That brings us to Section 3, how to keep your edge and rebuild that cognitive muscle.
This right here, this is the golden rule. It's the core philosophy you absolutely must adopt to survive today. Do the thinking before the prompt, not after the output. You see, evaluating AI output is a skill that just naturally degrades if you don't maintain it. Generating code? Sure, that can absolutely be delegated to an AI. But the engineering specification, anticipating the edge cases, the architectural judgment, those absolutely cannot be delegated. If you outsource the foundational design, you're literally outsourcing the exact reasoning that makes you a great engineer in the first place.
So here is a really brilliant, simple 80-20 framework to fix this without giving up your AI tools. Use AI freely for production speed, for sure, but carve out a deliberate 20% window for raw, unassisted practice. First, set up a daily 45-minute no AI coding window, just to keep that crucial muscle memory alive. Next, make it a habit to explain your goal out loud or type it out before you prompt the AI. Third, treat the AI's output exactly like a junior engineer's pull request. Read it line by line, scrutinize the whole shebang, and find the bugs. Fourth, always sketch your system designs on a whiteboard first before letting an LLM generate the architecture. And finally, when something breaks, actively debug it yourself before your brain instinctively goes, "Hey, AI, regenerate this?"
Once those skills are sharp, it comes down to Section 4,
choosing your AI path. This is arguably the highest stakes career decision you'll face.
If you're aiming for frontier labs like OpenAI, Anthropic, or Google DeepMind, where the acceptance rate is a famously brutal 0.5%, you really have to know where your specific talents fit. It basically comes down to this. Are you a builder or a discoverer? A research engineer is fundamentally a builder. They're brought in to make incredibly complex theoretical ideas work reliably at massive, unprecedented scale. They're deep in the trenches, debugging distributed systems that very few people on Earth have ever even seen. A research scientist, on the other hand, is a discoverer. They decide what the lab should actually focus on next. They navigate all this vast ambiguity, they dive into the latest theoretical papers, and they essentially define the future.
Let's look at how this plays out in the actual hiring pipeline. On the scientist track, research scientist roles almost universally require a PhD and a really strong track record of peer-reviewed novelty. Their interviews lean heavily into theoretical depth, research taste, and intense paper discussions. Contrast that with research engineers. They have slightly higher acceptance rates, though, let's be real, it's still wildly competitive, and their interviews focus intensely on machine learning system design and raw production coding. You don't necessarily need a PhD to be a builder, but you absolutely have to prove you can train huge models at an extreme scale.
But beyond just crushing leak code or system design, what are these top labs actually looking for when you're sitting in the room with them? Take a look at Anthropic's hidden criteria. Sure, they test for research intuition and taste, but arguably more importantly, they test for epistemic honesty and intellectual humility. They're looking for what they call calibrated uncertainty. Basically, if they push you to the absolute edge of your knowledge during an interview, the best thing you can possibly do is say, I don't know the answer to that with complete confidence, but here's how I would reason about it from first principles. Speculating wildly just to sound confident, that'll get you screened out instantly.
All right, moving beyond AI, we reach our final section, the quantum horizon, the next major financial and computational frontier. Consider this incredible number, 13,000 times. Back in October 2025, Google's 105-qubit Willow processor finished a highly complex computational task 13,000 times faster than the absolute best classical supercomputer available. To put that into perspective, a task that would have taken a grueling 3.2 years on a traditional supercomputer took this quantum chip just over 2 hours. Insane, right?
This kind of breakthrough leads us straight into a concept known as quantum advantage. This is that critical, paradigm-shifting threshold where a quantum machine outperforms a classical one in accuracy, cost, or efficiency. And it's super important to understand that this isn't just an incremental speed boost. It's not like simply buying a faster processor for your computer. Quantum advantage is an entirely different computational paradigm, one that can effortlessly solve structural problems that standard computers could literally never resolve, no matter how much time or electricity you gave them.
Here's a quick look at why it actually works. Classical hardware, which powers everything from the smartphone in your pocket to today's most advanced AI models, runs on bits. These are just electrical sequences that strictly resolve into a binary state, zeros and ones. Quantum computing, however, uses qubits. Qubits leverage these incredibly strange, powerful quantum phenomena like superposition and entanglement, and that allows them to process deeply complex, multidimensional, probabilistic configurations all at once, rather than just one by one.
Right now, we're in the middle of an incredibly intense hardware race to figure out the absolute best way to build these quantum processing units, or QPUs. And there's no single winner yet. We're seeing wildly diverse architectures fiercely competing for true commercial viability. You've got superconducting processors championed by tech giants like IBM and Google, squaring off against trapped ion systems by IonQ. Meanwhile, you have photonic architectures being developed by PsiQuantum and neutral atom systems being pushed by Pascal. It is just an all-out sprint to the future.
But let's ground the hype for just a second. You actually don't need a fully fault-tolerant universal quantum computer to see massive benefits today. The near-term path for the industry is actually hybrid quantum classical computing. Major financial institutions are already jumping all over this. Vanguard, for example, is already exploring hybrid systems to handle complex portfolio optimization under real-world liquidity constraints. And HSBC recently saw a staggering 34% improvement over their current models when predicting trade executions using quantum algorithms. So, the future? It's already leaking into the present.
Which brings us to our final thought today. We've traveled from multi-million-dollar cryptography salaries, we've navigated the subtle traps of AI coding tools, and we've peered over the edge of the quantum horizon. But honestly, none of that matters if you aren't preparing yourself properly right now. So I'm going to leave you with this challenge. Take a hard look at the tools you use every single day. Is your daily workflow building your future cognitive muscle, or is it quietly erasing your foundational skills? Think about it. Thanks for joining me on this explainer. Keep learning, keep practicing, and I'll catch you next time.